Welcome. We are the NOx valorization team. We're just going to take a second to introduce ourselves.
Hi, my name is Youngin Choi, and I'm a fourth year studying Oceanic and Atmospheric Sciences at UC San Diego.
Hey, I'm Priyan Sharma. I'm a second year master's student at Georgia Tech doing my environmental engineering degree.
Hi, I'm Sophia Yu. I'm a third year student studying chemical engineering at Vanderbilt University.
And I'm Zoe Zwecker. I already introduced myself, but I'm a fourth year at Colorado College studying environmental science.
So what is NOx valorization and what role does it play in the MIR project? Our group attempts to address these three problems: rising temperatures, global food insecurity, and an incircular economy. So with warming temperatures comes inhospitable conditions for humans and other organisms. It will worsen current ecosystems and cause extreme weather conditions. Rising temperatures will also lead to an increase in difficulty in traditional agricultural techniques, contributing more to global food insecurity when compounded with exponential human population increase. Concerning global food insecurity, the UN projects the world population to increase to 11.2 billion by the end of the century. If trends continue, it's projected that 840 million people will experience food insecurity, and that would be 9.8% of the global population. Finally, resources and elements in nature exist in cycles and loops. One of the main problems lies in the NOx cycle, which we aim to fix in this project. The solution to address the three problems, as discussed in the last slide, lies in recognizing NOx to be a valuable resource, which is how we can shift to a circular economy. So rather than reducing NOx emissions into atmospheric N2, we can convert it into HNO3 or HONO by using NOx capture technology. Then we could re-emit to offshore lands, which would remove pollution from urban centers and help to lower global temperatures. Then we could target food insecurity by utilizing an energy efficient conversion process to convert NOx into ammonia using a process that does not utilize the Haber-Bosch cycle.
So our current nitrogen loops are not very energy efficient, and the continuous burning of fossil fuels and other human activities have led to two partial nitrogen loops in series as depicted in this diagram. The first is the creation of NOx through fossil fuel combustion, and that is usually reduced back into nitrogen through selective catalytic reduction. The other process is using nitrogen to create ammonia through the very energy intensive Haber-Bosch process. And we are aiming to get rid of the Haber-Bosch process to create a more circular nitrogen loop. So this is the energy diagram depicting these two processes with the Haber-Bosch on your left and the selective catalytic reduction on your right. And you can see that there is a gap in NH3 and NO that we want to bridge. So our proposed solution is to connect NOx and ammonia through new chemical processes. And this current process that we're going to look into is electrochemical synthesis. This updated energy diagram shows where we're trying to bridge the gap and how we'll effectively consume less energy than the series of loops that were previously discussed. And like I just mentioned, the new process will be focused on electrochemical synthesis. So our presentation is going to focus on three aspects. The first is the NOx inventory, which will assess how much globally activated nitrogen is emitted. Secondly, we're going to focus on NOx uses. So how can we convert NOx into ammonia and urea for fertilizer? And third, we're going to talk about the atmospheric chemistry behind NOx's cooling mechanisms.
Cool. Talking about NOx inventory and capture, this will be discussed by Young and me. Moving on. So as we discussed, this is the loop that we are aiming for. So just to be clear, All of the NOx sources which come from combustion of fossil fuels are termed as sources over here, and the sinks would be ammonia, urea, and ammonium salts and nitric acid, which are denoted as NH3 plus over here. So we'll be discussing the source, but this is a general roadmap of what we are going to discuss. We talk about the source and the capture, then we talk about how the reusable NO and NO2 will be used as ammonia, urea, and nitric acid. Nitrogen inventory. So through rigorous calculations and analysis, we have come to the understanding that the sources that we have before reduction lie between the range of 4.16 to roughly 16 teramoles of active nitrogen per year. And there's a lot of vagueness in this because this data is collected from research papers and government records, and they are often conflicted in what they are reporting. And the sinks, on the other hand, are fairly certain because they're projected by industries, and we have a sink of 7.18 teramole of nitrogen per year. Next slide. But what I'm trying to focus over here is that we have a sink fulfillment of roughly 60% to up to twice the sink fulfillment over here if we just use NOx, which is right now a discarded resource to make ammonia and fertilizers for ourselves for food security. Another major thing that I would point out over here is that not only would we save the NOx being used as a pollutant, but in fact, we would be saving a lot of energy that is just discarded during the SCR and Haber-Bosch process. The inventory was created through the following method. The emission data was collected from public records and research papers. Then we looked up the policies that are being used in the countries, so we could work our way up to a global raw emission inventory so that we know how much NOx is being produced before it is being reduced by those current existing techniques. And I think now we'll move on to capture.
So now that we introduced our source in our nitrogen inventory, we'll move on to how we can capture the active NOx emissions with the use of capture technology. So one promising capture technology is wet scrubbing, and wet scrubbing uses ammonia to remove sulfur dioxide and NOx pollutants from flue gas, and NOx mostly exists as nitric oxide in coal-fired power plants. So to summarize the experiment that we looked at, we decompose hydrogen peroxide over an iron catalyst to produce Hox radicals, which you can see in the leftmost box. And then the Hox radicals oxidize the nitric oxide pollutant to a more soluble form, NO2, for absorption in the wet scrubber. And from the rightmost box, we can see that there are ammonia-based absorption products. So there are some points about the technicalities. This process is very efficient as the temperature and pH for a catalytic reaction is in the range of the flue gas that leaves the coal-fired power plants. So we don't need any additional steps to change the temperature and pH. And additionally, removal efficiencies for NOx and SO2 are 91.4% and 100% respectively.
So now we're going to focus on these new technologies to reuse NOx as a resource. So we've already established how much globally activated nitrogen we have and potential capture technologies using hydrogen peroxide. So now we're going to shift towards how exactly we can reuse the NOx to convert into nitrogen-based fertilizers. So global ammonia production is currently over 200 million metric tons, with it continuing to increase to almost 300 million metric tons by 2030. This is important for us to consider because 90% of this ammonia that is produced by the Haber-Bosch process is used for fertilizer. The main technology we're going to focus on to convert NOx into ammonia is electrochemical ammonia synthesis. There are a variety of pathways that this can go down, as in the ways that the atoms are hydrogenated, but the most efficient one based on this literature review is the ADHO pathway. Next slide. So the ADHO pathway involves hydrogenating the oxygen atom in NOx until we can form a nitrogen absorbate and water as a byproduct. And that is the rate determining step. After that, the nitrogen absorbate will be continuously hydrogenated until aqueous ammonia is formed. And this is conducted over a copper foam catalyst cathode. So this is the same energy diagram that you previously saw in our introduction, but this time it accounts for the activation energies needed for converting NOx into ammonia through this electrochemical ammonia synthesis process. And as you can see, the rate determining step has an activation energy that is significantly lower than the Haber-Bosch reaction process, and also just the general activation of nitrogen into NO through fossil fuel combustion. So with the previously discussed capture technology and electrochemical synthesis processes that show potential for improved energy usage, the first pathway we could go down is directly using NO2, which we have methods of directly isolating from flue gas, and that can be reacted with carbon dioxide through another electrochemical process to directly form urea. The second pathway that we have a knowledge gap in that we don't know how to directly isolate NO from flue gas, and that is something that should be further investigated. But assuming we can isolate pure NO, we can do the ADHO pathway previously discussed to form ammonia, and that ammonia can be used as pure ammonia or further synthesized into urea.
Okay, so Sophia just spoke about some of the direct uses of NOx, and now I'm going to talk about the indirect cooling mechanisms that NOx can have in our climate. So first, we can think about capture and re-emission of NOx, and this has the potential to have multiple climate benefits. And also, if we later consider the way that NOx can deposit, impact marine fertilization. So now we can begin to understand Earth's warming. So incoming shortwave radiation warms the Earth, which is represented by Q, heat. This heat is then radiated out by infrared radiation, which because of greenhouse gases often gets trapped in the atmosphere. Now we can begin to apply this concept to methane, which is a potent greenhouse gas. Methane is emitted from multiple sources, but for the purpose of this presentation is going to be represented by cattle. This shows our current works in an unclosed loop. As a greenhouse gas, methane shows the flux of outgoing IR radiation. So then also when thinking about how to close this loop, we can also consider all the fluxes into the source. So in this case, we're also considering carbon dioxide and the feed. Now that we know that methane exists in a partially unclosed loop, we need to better understand the problem with methane. So in the past decade, the concentration of methane has been on the rise. While making up 16% of all greenhouse gases, its 100-year global warming potential is 28 to 36 times that of carbon dioxide. So this graph shows a positive trend, but it kind of fails to tell us why this might be. So now we can look at this bottom graph, which shows the isotope ratio of carbon-13 to carbon-12. And this provides important information about the sinks of methane. So what can we do? We increase the concentration of the hydroxyl radical, which kills essentially methane. This slide shows all of the technical details of that oxidation process. It's pretty complicated with many intermediate steps. I just wrote 2 of them here. But the key takeaway is that it produces carbon dioxide and the hydroperoxy, which is important because it regenerates NOx and ozone, which means that it happens in a cyclical process. This figure, which is taken from the Jacobs textbook on atmospheric chemistry, does a really good job of kind of detailing the relevant chemical constituents in tropospheric chemistry. So first, just to back up a little bit, NOx is a high energy form of nitrogen, which is produced in high temperature environments. And it's relevant here because through photochemical reactions, it produces ozone. Again, through photochemical reactions, ozone produces the hydroxyl radical. And the hydroxyl radical is really what's key to this presentation. We can think of it as kind of the vacuum cleaner of the atmosphere, because it's defined by its oxidizing capacity. So just to reiterate, the concentration of the hydroxyl radical depends on NOx. So now, we can look at this, and we found a bunch of models that kind of suggest this cooling radiative forcing from methane oxidation to be between -1.4 and -10.8 milliwatts per meter squared per teragram of nitrogen that's emitted per year, which is kind of a complicating metric. But this is just one of the ways that NOx can impact the cooling of our atmosphere. Another I'll talk about right now. So this is just going back to the diagram on loops, and now we can see that through oxidation, we can close the methane loop. So moving on, NOx can also have positive climate impacts with aerosol formation. Aerosols are complicated, and I won't begin to suggest I know everything that's happening here. But this graph shows both the problem and potential with aerosols. We already talked a little bit about how aerosols mask about 1 degree Celsius of warming on the Earth, which is kind of scary, but also shows that they have great potential to help harness cooling mechanisms. So models suggest that the effective forcing of aerosols is about -1.6 watts per meter squared. Again, there's a lot of uncertainty with aerosols. We can see here that the error bars with aerosols are really large in comparison to other greenhouse gases like methane and carbon dioxide, which have a warming effect. So how exactly do aerosols relate to NOx? Through the production of the hydroxyl radical and interaction with volatile organic compounds, we are able to have condensation and nucleation happening, which impacts radiative forcing through the formation of aerosols and sometimes even cloud formation. So here's our updated diagram again, and we can see that this shortwave radiation is being reflected by aerosols. So what this does is we're decreasing incoming energy, which is the source, and we're increasing the flux of outgoing infrared radiation, which was previously inhibited by methane. Moving on, we can think about the ways that NOx is depositing. So we're thinking about marine nitrates. At this point, this left-hand loop should be pretty familiar, and now we're going to move on to this loop on the right, shown in the dotted line. So NOx can deposit in the form of nitrate, which is beneficial in marine environments and can help us scale marine agriculture. If we scale the production of seaweed in the Earth's oceans, we're able to feed it to cattle. And because of the makeup of seaweed, which is more protein rich rather than carbohydrate rich, cows release less methane, which therefore decreases our source potential. Here is a diagram again of kind of all of the goals of our project combined. The first over here on the left shows the inefficient processes in which we use Haber-Bosch to create ammonia from NOx. And then kind of in black and brown down here, we can see the potential to scale hydroxyl radical production to oxidize methane. And lastly, over on the right-hand side, we can think about the deposition of NOx in the form of nitrate to scale seaweed and marine agricultural production. That's all. Thank you so much.